In this video, we describe the wave function solution to the Schrodinger equation for the hydrogen atom. Alright, so this is how the hydrogen atom looks like. You have a nucleus and then one electron in the periphery of the nucleus, and we're trying to understand what the motion, the behavior of that electron is in that periphery. Now, in prior videos, we have set up the Schrodinger equation, we have solved it, and then we have examined the quantum numbers that appear in those solutions, and then we have looked at the energy solutions. In this video, we'll concentrate on the wave function. Something that is important is to recognize that when we were setting up the Schrodinger equation, we actually have chosen to solve the Schrodinger equation with spherical polar coordinates as opposed to Cartesian coordinates. A reminder of what that is: any point in space, if this is the nucleus and that is where the electron is, any point in space, that location can be specified with three Cartesian coordinates, x, y, or z, or what we call spherical polar coordinates, which is a distance from that electron to the nucleus, and then two angles, theta and phi, polar angle, and an azimuth angle. Okay, so r, theta, and phi, they uniquely determine the position in space of the electron, much as what x, y, and z would do, but it's more convenient to solve the expression using these polar coordinates. Because we're using those polar coordinates, then the solutions, the wave functions, are also going to depend on those polar coordinates r, theta, and phi. Okay, so let's take a look at what those solutions would be. It turns out that again, those solutions are going to depend on those three coordinates that we're choosing. Okay, one distance, and then two angles. Okay, and actually, what happens here is that that wave function is a product of two types of function. One of them that only depends on the distance, we call the radial function. Okay, and we're going to call it r of r. And then a function that depends on the angles theta and phi. Okay, which is what we call the angular part. This angular part can be written as simply one function or as two functions. Okay, one depending on each one of the angles. Okay, capital Phi depending on the angle phi. Alright, so again, this is the radial part and there is the angular part. We're going to talk about each one of them in turn. Okay, so let's take a look at the radial part. The radial part specifies how the wave function changes as you move away from the nucleus. Okay? Alright, so usually the wave function by itself doesn't tell you much. What we actually like to do is examine the wave function squared, because that is related to the probability of finding the electron in a given region of space. Right, so in the case of these wave functions for the hydrogen atom, instead of looking at r squared only, it's actually much more advantageous to look at something that is called the radial distribution function. Okay, RDF, the radial distribution function, is simply 4 pi r squared over r squared. Right, so notice that that would be simply the radial part of the wave function squared. So we recognize that this depends on probability, and the question is, well, what is this then? Well, this is something that is allowing us to calculate probability in a shell at a given distance from the nucleus. So the idea is as follows. Here's where the nucleus is, and that is where the electron might be. What we're asking is, what is the probability of finding the electron in a shell that is at that distance from the nucleus, but incorporates all possible directions, all possible angles around the nucleus. Okay, so think about the hydrogen atom as a perfect onion, and again, what we're trying to calculate here is what is the probability that the electron will be in onion shells at different distances from the nucleus. Okay, in the entire angular region, not only one direction, that's not what we're asking, but in all regions possible at a distance r from the nucleus. Okay, so that is actually calculated with something that we call the radial distribution function. Right, so then let's take a look at how that radial distribution function looks like for the most common solutions, okay, those solutions of lowest energy. Right, so the first solution to the Schrodinger equation is going to be the 1, 0, 0, which is what we call the 1s orbital. Okay? And the radial distribution function for the 1s orbital looks something like this. Okay, this is what we call the RDF, which is simply this function, and then as a function of the radius, okay, or the distance from the nucleus, from the electron to the nucleus, and this function looks like this. Okay, so it's a function that where the maximum probability is at this point, And this point happens to be something that is called the Bohr radius, A sub naught, which has a very well-defined values. Okay, so what we actually see is that, well, the wave function goes to, the radial distribution function goes to 0 at the nucleus, and then it slowly decays as you go, as r becomes greater. Right, so that is how the radial distribution function is for the 1s, and again, the electron is most likely to be at a distance of a naught, which is the Bohr radius. The value is about ½ angstrom or so. Okay, but what is interesting in these graphs is actually to compare this to other orbitals. Okay, so for example, now we can use this to understand the difference between the 1s and the 2s orbital. Okay, so the 2s orbital would be the orbital in which the principal quantum number is 2, but the angular momentum quantum number and magnetic quantum number do not change. Okay, so how would be the 2s radial distribution function? Well, the 2s radial distribution function is going to look like this. Okay, so you're going to have something like that. Okay, and this is how it looks like. This is the 1s, that is how the 2s looks like, and there's various differences. For one, you can clearly see that the 2s extends further away from the nucleus than the 1s. Okay, and this is something that is important, because we said before that the principal quantum number determines the size of the wave function, the size of the orbital. Okay, the only difference between the 1s and the 2s wave function is in the principal quantum number. Okay, or the main difference is the principal quantum number, and we see that that is the case, right? That principal quantum number tells you that this orbital extends farther from the space than the 1s. Something that is also very important is to recognize that at this particular point we actually have a node. Okay, so while in the 1s radial distribution function there's no nodes, okay, in the 2s you actually have one node. Okay, and then we can actually try to see how the 3s radial distribution function would look like. What we should expect to find is then radial distribution function that extends even further than the 2s, and it actually has one more node than the 2s, so that would be 2 total nodes. Okay, so for the 3s, what you should expect to find, I'm going to draw it separately, just to not confuse things. Okay, that would be the RDF for the 3s orbital should look like something like this. All right, where this extension would be larger than the 2s and the 1s, and you would actually find 2 nodes, and that's where the probability is 0, because the wave function is 0. Okay, that's what will the real distribution function for the 3s wave function would look like. Right, so again, notice that this is something that we're learning about the electron in the hydrogen atom, but just analyzing the radial part of the wave functions. And again, we see how these real distribution functions that tell us about probability, okay, change with the principal quantum number. Now what we can do is actually see how these radial distribution functions change with when you actually change the angular momentum quantum number. Okay, so this quantum number right here. All right, so let's take a look at various solutions right there. All right, so we can go to the 2 series. Okay, so we can compare what is the difference between the 2s and the 2p radial distribution function, RDF. Okay, and here we could choose any one of those. They actually all have the same size. The only difference is that they are oriented differently. So the -1, 0, and 1 have exactly the same radial part. Okay, so we don't have to worry about those. All right, so we know that the 2s radial distribution function looks something like this, and the 2p is going to look like this. That is the 2s. And the 2p is going to look like that. Right, so the difference is that the 2p actually has no nodes between 0 and infinity. Okay, but the extension of the wave function is actually about the same for the 2s and the 2p. Okay, that is because the angular momentum quantum number does not determine the size of the orbital to as large an extent as the principal quantum number does. These two wave functions have the same principal quantum number, so their size is going to be about the same. There is a difference in the number of nodes that you actually have right here, where the 2p doesn't have any nodes. Now, if we were to plot here the 3p radial distribution function on top of this one, what we should expect to find is that the 3p would extend further than the 2p, and it would have one more node than the 2p. For the 4p, what will happen is that that would extend even farther, and it will have 2 nodes. okay, and so forth. That would the number of nodes will continue to increase as you move to even larger quantum numbers. Okay, and this is essentially what the radial distribution functions look like. Okay, for a variety of states right here. Finally, what we can actually then do is try to talk about the angular part of the wave function. Again, the total wave function is divided into two parts, the radial part and the angular part. Until now, we've only talked about the radial part, okay, in terms of radial distribution functions. Okay, but we haven't said anything about the angular part. Well, the angular part only tells you how these wave functions change as a function of the angle. Okay, so suppose that you have you're at the distance r from the nucleus. What the angular part is going to tell you is how the wave function changes as you move in this direction or in that direction with those two angles. Okay, so we can actually perhaps see this a little better by writing the full wave function for the 1s orbital. Okay, so psi of 1s looks something like this: 2 over the square root of a naught thirds, and then e to the minus r over a naught, and then 1 over the square root of 2, 1 over the square root of 2 pi. This is the angular part. Notice that that is the one that depends on this r, and this would be the angular part. Okay, that would be your psi multiplied by phi. Okay, so what do we learn about the angular part for the 1s orbital? Notice that the angular part is actually constant for the 1s orbital, right? Notice that there's no variation on any theta angle or any phi angle. What that means is that at a distance r from the nucleus, if you sweep the angle, okay, either this angle, the azimuth, or the polar angle, okay, the orbital doesn't change shape. If the angular part is constant, that means that again, changing the angle does not change the shape of the orbital. Okay, in other words, this means that this orbital that we call 1s is actually spherical. Okay, that's what the angular part tells you. If we were actually able to write here what the angular part would be for, say, a 2p orbital, okay, we will see that actually it depends on the angle. Okay, so that is what confers the p orbitals the lobe shape aspect that you guys have seen in other courses. Okay, and again, that is determined solely by the angular part that now would depend on this angle and on that angle. And then for the d orbitals, what happens is that you have other dependence on the angle, and that is what gives those d orbitals cloverleaf shape and so forth. Okay, so in summary, what we've done in this video is try to take a first look at how to analyze, how to think about the wave functions in the hadron atom. What we have learned is that the orbitals that we have used in other courses, the 1s, the 2s, the 3s, 2p, 3p, 3d, all those are simply solutions of the Schrodinger equation for the electron in the hadron atom. Okay, and as such, they have two things that you have to worry about. One of them is the energy, which you have examined in a different video, and the other one is the wave function. The wave function by itself doesn't tell you much, but if you square it, then you can obtain probabilities. Okay, so for the case of those wave functions in the hadron atom, for those orbitals, we actually have seen that the radial part codes how the wave function changes as you move away from the nucleus. Okay, that's what the radial part is, and again, study of the radial distribution functions tells you the number of nodes you have along the radial direction and the extent of that orbital. Okay, the angular part of the wave function tells you how the orbital changes in shape as you move according to these two angles that we have specified right here. And that is what determines the shape of the wave function, again, around these angular directions. Okay, so for s orbitals, it turns out that the angular part is constant, so that leads to spherical symmetry. For p orbitals, you have a complicated dependence that gives you this lobe shape. For d orbitals, you'll have a dependence on these angles that give you a cloverleaf shape. Okay, so this discussion kind of wraps up our knowledge of the hadron atom, and then in prior videos we will actually move to atoms that have more than one electron.